In this video, we have to see the design of gantry girder. Here you can see the image of gantry girder. So this is the gantry girder. Here you can see the side sections, right? These are the gantry girders. And in between it is a crane girder, it is called as, and it is a trolley. You can see this trolley is carrying a hook, so sometimes it will be having a cabin which can be moved along this crane girder, and again this crane girder can be moved along the gantry girder. So it can shift the loads or it can transfer the loads along the area, along some particular area depending on the size of the crane girder and gantry girder. So let us see the design of it. So directly we can go for design. So this is the question. Design a simply supported gantry girder to carry an electric overhead traveling crane. Given span of gantry girder is 6.5 meter. So here gantry girder span. So this I section, length of this I section is 6.5 meter is given. Span of crane girder 16 meter. So this crane girder length is 16 meter. Crane capacity is 250 kilometer. That means this crane girder can carry 250 kilometer of load. Here self weight of the crane girder excluding trolley is 200 kilometer. So only crane girder except this trolley it is having only 200 kilometer. Of course this is UDL completely, but we overall together it is 200 kilometer. Self weight of the trolley, we can also call it as a crab. So this is a trolley and its own self weight is 50 kilometer. Minimum hook approach, that is the minimum distance it can have from the gantry girder is 1 meter. Distance between wheels is 3.5 meters. So here you can see the crane girder. This is one wheel, this is one wheel. So in between it is 3.5 meters. Self weight of the rails 0.3 kilonewton per meter. So here we have to go step by step. So totally it is having 12 steps. So firstly we have to calculate the moments due to vertical loads. In the second step we have to calculate the moments due to horizontal loads. Here maximum moment due to horizontal loads we have to calculate. In third step we have to calculate the shear force. So in fourth step we have to assume the preliminary section based on the values we got in the previous steps. And in the next step, we have to find out the plastic modulus of the assumed section. So in the step 6, we have to find out check for moment capacity. Now onwards the checks will start. Here one check is for moment capacity. In step 7 is a check for combined local capacity. In step 8, check for buckling resistance. In step 9, check for biaxial bending. In step 10, check for shear. In step 11, it is weld design. Step 12 is again for buckling check, and last one is check for deflection. So after that, it can be completed. So let us see all of them in one by one, all the steps one by one. Let us come back. Here step 1, we have to find out the moments due to vertical loads. So we have to find out the load first, for which we have to calculate the maximum moment. So the load is weight of the trolley plus crane capacity. I will show you. Is weight of the trolley plus the load it can carry together. The more load we have to consider for maximum moment. So self weight and also another load we have self weight of the crane girder. This is also having some weight which is falling on the gantry girder, right? So it is also having some self weight. We have to take it as 200 kilometers. Here I have tried to draw the diagram of this. Here this is one wheel, this is one wheel, there's a crane girder which is having 3.5 meter as given in the question. I have drawn distance between wheels, and this is the length of the span of the crane girder 16 meter, and this is the length of the gantry girder. This is 6.5 meter as given in the question itself. Here span of the gantry girder. This is the span of the gantry girder, and this is span of crane girder 16 meter. This is span of crane girder 16 meter, right? So we have to now find out the maximum reaction on gantry girder. The moving load should be as closer as possible to the gantry girder. So what is the maximum possible closeness? So this is 1 meter apart. You cannot go beyond that. So the maximum, so totally 300 kilonewton, right? What is that? This is this crane cabin, I mean trolley, plus the weight it can carry. That's together 300 kilonewton. That should be very near to the support in order to get the maximum reaction, isn't it? So we are choosing reaction support A to get the maximum shear, I mean the maximum reaction. So 300 kilonewton, this should be 1 meter because it is given as minimum hook approach. So that is the closest distance possible from gantry girder. It is just 1 meter itself. Okay. So we have to now find out the reactions RA and RB. So what we have to do? So generally we have to consider. So all moments about point, any point should be 0. So for example, I will be taking sigma MA is equal to 0. All moments about point A will be 0. So what are the moments we have? RB into 16. This load which is anti-clockwise we are taking as it is positive. So another load 200 kilonewton. Of course I have shown it as UDL. But together overall gantry girder weight is given as 200 kilonewton. So that is point load. We are assuming it to be acting at the center of this span. Okay, that is 200 into half of this length, that is 16 by 2, which is 200 into distance 16 by 2. It is acting in clockwise direction, so it is negative. And another load we have 300 kilonewton into 1 meter distance. 300 into 1, it is also clockwise, again minus is equal to 0. So what we get here? So RB into 16, these terms will go right side. 200 into 16 by 2 into plus 300 into 1. So we will be getting RB into 16 as 1900. So that is RB we will be getting it as after dividing it with 16 we will be getting 118.75 kilonewton. So we have to also find out RA. So let us find out. How will you find out the total load? All the loads which are acting downwards should be equal to the loads or sum of all the loads will be equal to 0, or all the vertical loads will be 0. Sum of all vertical loads will be 0, or the loads acting downwards should be equal to the loads acting upwards. So RA and RB which are acting upwards, and we are having two loads 300 and 200 kilonewton, that is 500 kilonewton. So this is the total load acting on the span. So how will you find out RA? RB we have got it as 118.75. So total load minus RB will give you RA 381.25 kilonewton. This load is transferred to gantry girder through two wheels. So load on the gantry girder from each wheel is 381.25 by 2. So this load will be shared by not only one part. This reaction has two wheels. So as I have shown you, so wheels are there 3.5 meters apart. This wheel is sharing some load, this wheel is sharing some load. We are sharing them equally. So whatever the load we got at the support will be shared to the loads, two wheels. That is 381.25 by 2. We will be getting it as 90.63 kilonewton. So that is the load we have to consider. But we have to consider the factored load possible, which is multiplied by 1.5. That will give you 286 kilonewton. So now the maximum moment due to moving loads occur under a wheel when center of gravity of the wheel and the wheel are equidistant from the center of girder. Now this is the girder diagram. I will show you. So now we have found there's a simply supported beam. We have got all the shear forces. We have got the reactions, right? Now we are taking this span, and this condition is gantry girder span, which is 6 meter. Let me write this span of gantry girder. Okay, what it says, the maximum moment due to moving loads occur under a wheel when the center of gravity of wheel load and wheel are equidistant from the girder. So center of gravity of the wheel load, and that means center of gravity of this and wheel are equidistant. This is the center. Okay, this is the wheel and this is the center of gravity of the wheel. So they should be equidistant from the center. So how will you find out this total 6.5 meter? And up to this C center, this 3.25, 3.25. That's 6.5 by 2, 6.5 by 2. Now this is 3.5 meter. So 1/2 should be, 3.25 by 2 should be equal to the half of this, half of this load. Simply we can say this is the wheel load center and this is center of the span. Okay, so though there should be equidistant from the girder. So if you see this here, so automatically they will be equidistant. For example, this is 6.5 meter and this is 3.25, this is 3.25. So what is this? This total 3.5 meter. Half of that would be 1.75. 1.75 this side and half of 1.75 is up to the center and remaining part is of course half up to its end. Okay, and remaining this is calculated as this is 3.25 minus 1.75 minus 1.75 by 2 will give you 0.625, and similarly this also the remaining distance will be calculated as 2.375. So what is this through 286 kilonewton? This is the wheel load. One wheel it is carrying as 286 kilonewton. Another side also it is carrying 286 kilonewton. Wherever the wheel is there, that can carry the maximum factor load 286 kilonewton, and this is distance, wheel distance. Okay. So now we have to find out the reaction force considering it as simply supported wheel. So RA, similarly we have to calculate the reactions RA and RB. We have to consider the moments. Sigma MA is equal to 0, just like we have calculated in previous case. This is RA into, okay, sorry, RA1, let me say, because we have taken there, right? RA1 into 6.5 is equal to 286 into this distance. That would be how much? 1.75 by 2 is 0.875 plus this another 0.875 plus 1.75 plus 0.625. This is the distance. This is the load. This is the load into distance plus moment is actually load into perpendicular distance, right? So another load we have 286 into 0.625. So upon calculating the value of RA, we get it as 209 kilonewton. So together we know the all upward loads should be equal to the downward loads. Downward loads we have two wheel loads 286, and upward loads we got one load RA1 209. So we can now find out RA. From the total load minus RA1 we get it as 363 kilonewton. So up to that we have calculated the reactions. Now we have to find out the shear forces. So shear forces, you know this, right? This RA1. So this is RA1. This is RA. So previously we got it, right? This is at 0.625 we have 1 to 86, and here it is 1 to another 286 at the distance specified there. Okay, shear force right upward negative. So we are coming from this side to this side, right upward negative. So right upward force we have RUN, you know the shear force rule, right? Right upward negative. The force which is acting upward on the right side of the section is negative. So we are considering section just here minus 209 kilonewton, that is minus RA1 itself, this one. Shear force at C at this point we got this some of the loads we have to consider. Now our section transfers here minus RA1 plus 286, we get minus 77 kilonewton. Now this is point D, section shifts here. Now this is RA1 and the minus RA1 plus 286 plus 286, so we get it as minus 363 kilonewton. Of course that is RA. So maximum moment occurs at, of course, at E, at RE. Sorry, maximum moment occurs at E, point E. So that's a new point we have to consider. RA1, so BM at E, which is at this distance, E. At this point, we will be having the maximum moment. So we are directly calculating moment at there. It's simply RA1 into 2.375. Sorry, this is point E. Not E, it's C, not C. Okay. So RA1 we have the value as 209 kilonewton and 2.375 is the distance. Together we will be getting as this as a moment, maximum bending moment. So next we have to calculate the moment due to impact also. Because there will be some loads having suddenly it is carrying or leaving the loads. So there is definitely the some part will be there due to impact. So we are considering it as 25% of moment, extra 25% of the moment. So already we are having 496. So impact load only if you consider this 25 by 100 into the moment we got, that is 124.092. So let us assume the self weight of the girder as 2 kilonewton per meter. So this is only the assumption. Dead load will be now self weight of the girder, we are assuming it as 2 plus self weight of the rails. Because self weight of the girder was not given, so we are assuming. Later we have to check whether it is correct or not. So is the relevant assumption. So upload the girder with rails. Okay, I will show you. I will show you the image, you will understand. So this is the girder ice. Okay, this is the girder. This is the girder and this is the rail. This is the rail, this is the girder. So overall rail self weight was given. The girder self weight is not given. We are assuming it as kilonewton per meter. As given in the question, this is self weight of the rails. So together dead load will be 2.3 kilonewton, including what? Self weight of girder, self weight of rails. Now factor dead load would be 2.3 into 1.5. Multiply with 1.5. It will be the factor of safety. So you will be getting it as 3.45 kilonewton per meter. Now we have to calculate the moment due to dead load. So simply that is a dead load is a gantry girder, right? It is having the complete along the length it will be having. So it is like UDL. So the maximum moment for simply supported beam carrying UDL would be WL square by 8. So here what is the W? We just calculated the factor dead load 3.45 kilonewton per meter and L is the length of the girder. There is 6.5 meters span was given in the question, right? So upon calculating, substituting the values here, we will be getting that 18.22 kilonewton meter. Now factored moment due to vertical loads we have to calculate. So let us say this MZ. That would be total the maximum moment plus maximum moment due to impact, maximum moment due to dead load. So if what are the moments we have calculated in the previous steps, all should be summed up here. So totally 638.68 kilonewton meter. In the second step, we have to find the maximum moment due to horizontal force. So what we have got in the first step is a moment due to vertical loads. Here we have to find out the moment due to horizontal force. We can also call it as surge. What is that? The horizontal force transfers to the rails is 10% of the weight of the trolley plus load lifted. So due to this, the horizontal surge will occur sometime. So we are calculating it as 10% of the total weight of the trolley plus the weight it carries. So it is 30 kilonewton. So now we let us assume double flamed wheels. So double flamed wheels are nothing but you can see the train wheels, right? They will be like this. So rail will be like this and train wheels for us sitting like this. So this is called double flamed. Double flamed wheels. These are okay. So we are assuming double flamed wheels. 4 wheels will be there overall. That side 2 and this side 2 for the girder. So totally this 30 kilonewton will be shared upon those 4 loads, 4 wheels. So one wheel, another wheel, another wheel, another wheel. Okay. So that is 7.5 kilonewton is the load shared by each wheel. So now what is the horizontal force factor load? If you consider the factor of safety, multiply the factor of safety, we will be getting it as 11.25 kilonewton. So for maximum moment in gantry girder, the portion of load is same as shown in the figure, except that it is horizontal. So whatever we have calculated for vertical loads, it is also same. So what simply is, it is horizontal. What simply we have to do is, for 286 kilonewton of wheel load it is carrying, we got the moment as 496.375 as we have calculated previously. Now for 11.25 kilonewton which is horizontal, how much it would be? Combined. So that is we are doing cross multiplication. That's 496.375 into 11.25 by 286. So we are getting it as 19.525 kilonewton meter. Okay, that's it. And what we have calculated in step 1 and step 2. So step 1 we have seen moment due to vertical loads. In second step we have calculated moment due to horizontal loads, which is very simple. We have to take the cross multiplication from the already calculated vertical loads. In step 3 we have to find out the shear force now. So what is this 6.5? This is the span of gantry girder, not span of crane girder. Okay. And these are the wheels we are assuming it as 286 kilonewton, 286 kilonewton, and this is placed at distance 3 meter. So what is the vertical load due to shear due to wheel loads? This is we have already calculated 286 kilonewton. So now we can find out RA into 6.5 into 286 into 6.5 minus 3. So in this case, the gantry girder, so the crane, we are parking it at the very end, at the very edge of the gantry girder. For crane girder, we have the limit. For crane girder, we have this minimum approach 1 meter. For but not gantry girder. Gantry girder, we can place it up to the edge. So we are keeping it to the edge so that we can get maximum reaction at E. Right, wherever the load is there, we will be getting maximum reaction there, right? So assuming it as simply supported beam again, we have to calculate the moments about point A is 0, sigma MA is equal to 0. So A1 this is RA1 into 6.5 is equal to 286 into the load or the distance. What is this? 6.5 minus 3. So we get RA as 1.154 kilonewton upon calculating. So total load is total vertical loads are RA and RP. Total downward loads are 286 and 286. So what we get RA? 418 kilonewton. RA1 is 154. Is having very less, right? Okay, compared to this 418 kilonewton. The maximum reaction it can have when we park this crane girder here. Park this crane girder, of course, at the edge of the gantry girder. So now vertical shear due to impact, we are assuming it as 25%. 25% of impact, we are assuming it as 25% there also, right? So we are getting it as 104.5 kilonewton. Okay, now vertical shear due to self weight. So it is very simple. Vertical shear is just shear force we are calculating, assuming it as self weight is a UDL, right? Self weight it is completely spread on it. Okay, that is simply WL by 2. So what is W? That's a factor dead load of the gantry girder with wheels, 3.45 kilonewton per meter, and length of the gantry girder 6.5 meter. Well, we have this value WL by 2, 3.45 into L 6.5 by 2 to get it as 11.21 kilonewton. Now, what is the total vertical shear? So we have calculated this vertical load, the maximum vertical load due to impact, and this vertical load due to shear self weight, and the maximum vertical load due to the wheel load, due to this wheel. So three loads we have calculated. One is with impact, one is with self weight, another one is with, of course, the live load. Okay, 480 kilonewton. We get it as totally 533.71 kilonewton. That's the total vertical shear. Now this is also just like we have calculated moment due to horizontal forces. We have to consider the lateral shear due to such, which is a horizontal force. Here also the same thing, we have to do the cross multiplication. So for a 286 kilonewton of the weight load, we got the live shear force as 418 kilonewton. But 11.25 kilonewton of this horizontal load, what we have calculated earlier, how much we will be getting? So do cross multiplication and you will be getting it as 16.44 kilonewton. Step 4, we have to assume the preliminary section. Trial section we have to assume. So the trial section may be selected by using the guidelines. These guidelines we have to consider while selecting the preliminary section. One is the economical depth is about 1/12 of the span. Compression flange, which may be kept as 1/25 of span. The moment capacity of vertical load should be 40% more than the moment due to vertical load. So these are the points you need to remember. Let us try first. So what is the first case? 1/12 of the span. That is span by 12. 6.5, it is in meters, so we are converting into mm, into 1000 by 12. This is 541.7 mm. So let us equate it to 600 mm. Okay. Another one, what we have to try, compression flange, which may be kept as 1 by 25th of the span. So compression flange, okay, compression flange I have to tell you, right? What is, so this is the section we are considering. The section girder will be like this, and above that it will be having a compression flange, the rail. Okay, there's a compression flange which is the channel section, and this is the I section. Okay, rail. This is for economic depth is about 1/12 of the span. This is for I section. L by 25 compression flange. This is for this channel section. What should be that? L by 25. That's 6.5 into 1000 as mm, converted into mm by 12. We'll be getting it as 260 mm. So let us equate to 300 mm. So matching this, let us try ISWB, Indian Standard Wide Beam 600. As web and flange from the cross sections, sorry, I section, this I section, center and ISMC, Indian Standard Medium Channel Section 300 as a compression plane. This is ISMC, and this is ISWB 600. So from so this is the diagram we have drawn. This is ISMB 600. As I said, this is compression plane ISMC 300. So these are all the values we get, all these dimensions we get from the steel tables. So you can refer page number 4, table number 1, ISWB 600. You can see all these values there. Area, the width of the compression flange, thickness of the the flange, thickness of the flange, thickness of the web. There's a moment of inertia. There's a moment of inertia about both axes. So these are the properties of ISMC. We can see page number 6, table number 2 from steel tables. So these are all the properties of I section. All will be mentioned in that page. You can just refer that once. So after writing all these values, from now onwards, all our calculations will be based on the already mentioned values in the steel table. So you have to write all of this. So these are all the values we will be using. So first the section modulus is, you know section modulus, right? There is a moment of inertia by I by y. There is a depth from the neutral axis. Okay, we have to find out what is I. Okay, so first we get it as we have two I's. Okay, one is moment of inertia I z z. I by y we have to calculate AI into y1 bar minus y bar. So you know this value, right? You know this equation formula we will be calculating, you will be using to calculate the moment of inertia since strength of materials onwards, engineering mechanics onwards. So after writing this, we have to know what are all the parameters here. IXX, from this we got it. Area, we can directly get it. AI I have mentioned because this is for I section. And plus we have added this for channel section. For that I have mentioned this as C. Okay. AI is the area of this I section 17038. So total area, what we'll get? Area of I section in center of area of I section plus area of channel section plus centroid of channel section. So we have to write all these also. So AI we have 17038 mm square, AC 4564 mm square, Y1 is 600 by 2 because it's total 600 up to here. Half of this will be 600 by 2 and this YC is 600 plus 7.6. Okay, I will show you. 600 plus 7.6 plus is 13.6. Another value we will be having. I will show you what is the 13.6. Okay, 23.6. Sorry, this 23.6 will be there another value. That is in properties I have written. I will show you. Okay, this is centroid. Centroid is 23.6. This is directly mentioned in the steel table itself. You just add, subtract it. You'll be getting this. Getting it as 584 mm. Now you can find out y bar after writing all these values. After realizing all these values, you can simply find out the y bar. Substitute all the values we have written AI, YI, AC, YC. Okay, by AI plus AC. And you got it as 360 mm. So this is the Y bar. You got it as 360 mm where the centroid is located. Okay. Now IXX we have to find out. So for also this IZZ this AI into Y bar minus Y1 whole square. This is the same formula we have to use. IZZ from the question itself we got. Okay. And this is 17038. So these are all the values already mentioned. So I'm writing it here directly because all the values are mentioned. We have already calculated. So you'll be getting it as 1352.325 into 10 power 6. So why we have to calculate all this? So this is already directly mentioned. So we have to now find out the section modulus. In order to find out this, we are calculating this. So let us find out IZZ. So IZZ sometimes we mention it as this section Z, or sometimes we will mention it as section X because it will be considered it as, so generally this will be considered as X axis. This is X. This is Z. But as we are habituated to calculate it for 2D sections, sometimes we will be calling it as IXX. No issues of that. Okay, IXX by Ymax, you will be getting it as 3.756 into 10 power 6 mm cube as a section modulus. Now we have to do it for compression flange. I by Ymax. Only compression flange we have to consider. So this D1 B1 cube by 12 plus IZZ. So D1 is the depth of this, 21.3 is this one. Okay. Into, so this is a rectangle simply, 250 is its width. dB cube by 12 simply, dB cube by 12 plus IZZ. For C it is directly given in steel tables. We have already written there itself. Okay, so totally we will be getting it at 9.1. I by way we have to consider the part which is connected with channel section. So that is the only thing we have to add. Otherwise we can take directly this. As it is connected to I section flange, we have to take that flange moment of inertia also. Okay. Now ZEY for compression flange, we got it as I by Y. We got it as 609.069. Okay, Y max, you know that, right? 300 by 2. Why 300? There is a channel section length is 300 by 2. Okay. In step 5, we have to find out the plastic modulus of the section. Now you can see for plastic modulus in unit 3 we have taken another axis will be there. So there is not a neutral axis. The neutral axis we have already located here, right? Neutral axis at 360 mm. But now you can see neutral axis is having some another dimension. So that is actually plastic neutral axis we can call it as. We can also call it as equal area axis. So above the axis and below the axis, area of cross section should be same. So what is the total area of cross section? Generally we AI plus AC. So depending on steel tables, the properties we have written, we have added the total area of the section as 21602 mm square. So let the plastic neutral axis, equal area axis be at the distance YP from the center of flange. So YP, let us assume it as YP. Okay, equal area, that is total area is this 21602. That should be equal to, so area of this shaded portion. Area of this shaded portion. We can take this area also. But this is looking little hectic. So we are taking this area in order to calculate it easily. So what is that? This area, this rectangular area and this rectangular area. So what is that? The 250 into 21.3 plus 11.2 into this distance. What is that? How much would it would be? YP minus 21.3, this one. So that we will be getting this angle. So only unknown value here is YP. Upon calculating, we will be getting YP as 510.2. So this is the location where you will be get the plastic neutral axis, equal area axis. Now we have to find out the plastic moment. So which is the sum of moments of forces at yield about the plastic neutral axis. So we have to take all the moments about the plastic neutral axis. So sigma Ay bar into Fy simply. So 250, so this is the area. 250 into 21.3. This is area into distance. So what is the distance? So center of this to this neutral axis. So that is 510.2 minus 21.3 by 2. So this one into Fy. Okay, into this one again this area bottom web area into y bar distance from the neutral axis to this portion. Okay, bottom part is over. Now we have to similarly calculate the top flange. So this into area, center of axis, this into area of this into distance, and area of top web into distance. Okay, so we have calculated for bottom web, top flange, top web, top compression flange. So what we get? So Fy up to Fy we got it as 4686450 into Fy. Now let us find the plastic modulus, which is MP by Fy as a obtained value by Fy. Simply Fy is gone. Okay, that is only for reference. We got it. However, it will not be included in calculation, of course. Okay, 4686450 mm3. So there is a plastic modulus. We got it as for top flange. We have to calculate separately MP by Fy, just like we have calculated for separate sections. We have to do the same for this also. We'll be getting it as 824764 mm3. Okay, now we have calculated plastic moments. Now onwards the checks will start. So in step 6, we have to check for moment capacity. So from page number 18, table number 2 of IS 800. So you can find out these parameters. We can find out these conditions. If B by T of flange of ISWB 600 would be B by T. So this is 250 by minus 11.2. I will show you. This is 250 minus 11.2. So only outstanding flange by 2. Outstanding flange we have to calculate by 2 into 21.3. 2 into the thickness of the flange. So there is 5.6. It is less than 8.4. So D by T of web also we have to check for IS 600. So 600 minus as a thickness to two sides by thickness of the web, we get it as 49.76, which is less than 84. And B by T of the flange of the channel, so that is a 90 minus. Okay, 90 minus, there is a 90. It's like this 90 minus 7.6. Only outstanding link we have to consider by T, thickness of the channel. So we'll be getting that 6.06, which is again 8.4. So all these will indicate that it is a plastic section. It comes under plastic category. Or I will show you. Here you can see, as mentioned, the table number 2 is a plastic section. When for welded section, if it is less than 8.4 times E, epsilon is simply so epsilon is generally under root Fy by 250. So Fy we have calculated here for 250 grade, 250 by 250 will be 1. So we are not included that. So okay, this is the this comes under plastic category. So now this local moment capacity for bending in vertical will be given as mdz is equal to Fy into Zp by gamma m naught. Fy 250 Newton per mm square, Zp is we have calculated previously 4686450 mm cube, gamma m naught 1.1. So let us substitute it here in order to get the design moment. Okay, and we have to check the design moment with this. So this is also mentioned in the page number, is in the same page itself. Sorry, this is mentioned in 8.4.2 clause 8 of IS 800. You just check it out. 1.2 into ZE into Fy by gamma m naught. Let us check with this. So MdZ, whichever is the less value, we have to consider. MdZ, either this or this. So let us consider the lesser value. Design moment will be 854.127 kilonewton meter. Now let us check the moment capacity for the top flange. MdZ, the same value we have to consider. For ZP for top flange we have to consider. We have already calculated. Just write it. So we can find out MdZ, and again let us check with this expression also as we have done previously. Okay, substitute all whatever we have. We will be getting it as 166.11 kilonewton. For top flange, the lesser value again we have to consider up from 187, 166. Let us consider 166.11 kilonewton meter. Okay, let us check for combined local capacity. So this is the case. Mz by Mdz plus My by Md by less than or equal to 1. So here Mz is, we have already calculated factor moment due to vertical loads 638.689. Mdz we have just calculated 854.12. So My is 19.525. This is the maximum moment due to horizontal loads. We have calculated using this cross multiplication, right? That is. Mdy is Mdz of top flange. All are calculated. So we have to just substitute. So this is also mentioned in IS 800 clause 8, 8.4. It starts from 8.4 onwards. You just check it out. Okay, so it is adequate. It is less than 1. It has to satisfy. It can 0.865. So it is okay. So let us check step 8, the buckling resistance. So is a clause 8.2.2.1 IS 800. This is the case. MD is equal to beta B ZP FD. So FBD. For plastic section, beta B is 1.0. In the same clause it is mentioned. MD design moment would be ZP into FBD. So this FBD depends on what? Is FCRB. So FCR, this formula was also mentioned in the same page. All these parameters we have to write. So LLT is nothing but the span of the gantry girder, which is 6.5 meter. And we have the Young's modulus of is a minus still 2 into 10 power 5 Newton per mm square. HF is the height of the flange overall height. We have this compression flange like this, right? This overall I section is 600 plus this thickness is 7.6. So overall depth. HF is 607.6 mm. This is 600. This is 7.6. Okay. This thickness of flange 21.3. This thickness of flange is 21. We have already drawn all just for reference. I'm telling you. This is radius of gyration under root I by A. We got it right. We have two flanges and two sections. So add them both. We'll be getting it as. So area also we have channel section and I section. Mentioned in steel tables. We have already written it. Add them both. 21602. So from these two we can find out this radius of gyration. We have we just have to substitute there. 71.57 we got FCR. So we can now find out this FCR value. So substitute all the parameters. All the parameters were written here. Okay. You get 323.06 Newton per mm square. Table number 14 of IS 800. It can also be used to find FCR. So we have already done the similar kind of way. There are two methods. This method we can use, or we can also find out the KL by lambda value, slenderness ratio, and we can find out FCR value by doing interpolation. Okay. Okay. The page number 55 that gives the FBD depends on FCR. So there we can do the interpolation. So I have shown you this here. So if you do interpolation, so for 350 you have the value in that table as 172.7. Okay, I will show you. Page number 55. Okay, page number 55. FCR value, this is are very less. For 350, 300, the values will be there. Here this is 350, here this is 300. For 250 gray, we have written the values as this 170.2, 172.7 and 163.6. These two values. Our value, which is 323.06, is in between 350 and 300. So we have to do interpolation. What is that? 350 minus this and 323.06 by this. So 172.2 minus x by x minus 163.6. Upon substituting, upon solving, we get the value of x as 161.74, which is of course the FBD value 161.67. Okay, that we can use in order to find out the design moment. So just like we can use another table to find out FCR. So for this we have used this case in order to find out FBD, which we can use in finding design moment. ZP into ZP we have already calculated, just substitute that. FBD we have just calculated. So we got it as 758 kilonewton. It is more than the 638, which is the vertical shear. So it is adequate. So in step 9, we have to now check for biaxial bending. So this is a formula in order to find out. So all section 8 around we will be getting IS 800. You will be getting all these values here. MDY is Fy into Zy by gamma m naught. So we have all the values. Fy, the grade of steel, 215 Newton per mm square. Gamma m naught, 1.1 partial safety factor. Zy, Iy by y max. So Iy we have this value. We got it. Y max is this 115 mm. So upon substituting all the values, you will be getting the maximum design moment as 167.65. So now we have to check for this. We have already done. Okay, but the moment dy only changes here. So upon substituting, we have to make sure that is less than 1. So we are getting it as 0.959. It is less than 1, so it is adequate. Another step, step 10 is check for shear. Shear capacity AV into FYW by root 3 gamma m naught. So AV is the area of shear web, which is actually having this shear load. Okay, 600 into 11.2. 600 is the overall depth, right? This 600 into 11.2 is the thickness. That's 6720 mm square. FYW is 250 Newton per mm square. So upon substituting, what we get is shear capacity 881, which is greater than 533, which was previously imposed on it. We have calculated. So it is okay. 0.6 VD we have to check once. Okay, 0.6 of this design force. So it is 529. So it is slightly less than B. Considering it as high shear case may be ignored. Hence there is no reduction in moment capacity. Therefore, previously we have found moment capacity, right? That is enough. So even it is slightly less than, it is acceptable. It is just another calculation in order to check for more capacity. That's it. Okay, in step 11 we have to go for weld design. So design shear will be equal to the strength of the weld. So design shear Q, it is given as shear force by this moment of inertia about z axis multiplied by this centroidal area, I mean AY bar. So what we get here, shear force is of course V. We have calculated previously imposed on it by B into I, B by B into I into AY bar. Okay. So what we get here? So these are all the values we have already available. Area of the channel A here, 4564. Design strength, if you equate to the strength of the weld, you will be getting the size of the weld. So here we have to calculate design shear or shear force by unit length Q. Okay, substitute all these, you will be getting it as 484.6 Newton per meter. ES is the size of the weld. So strength of weld is generally given as 2 into K into S into Fu by root 3 gamma m naught. Page number 78, IS 800. Check it out. Okay. So you will be getting as 265.12 into S Newton per mm. So now equate the strength of weld to the design shear in order to get the strength of the weld. So 265.12 into S is equal to 484.6. So you'll be getting the size of weld as 1.83 mm. So minimum size welded to be provided is 5 mm. According to the table number 21, page number 78 of IS 800, you can see the table. Minimum weld size should be 5 mm. Percentage weld. Now we have to calculate. This is the size of the weld obtained, which is 1.83. Yes, minimum as mentioned in the code, this is 5. S obtained by S minimum into 100. 1.83 by 5 into 100, 36.6%. So let us provide 40% of weld with size 5 mm. And that means 40% means, for example, if 10 mm is there, you provide 10 centimeter, 40 mm, let us provide 40 mm and weld is provided and 60 mm gap. Again 40 mm will be provided, 60 mm gap is the intermittent weld. So page number 79 talks about this intermittent welds. You just check it out. Check for now. Step 12 is to check for web buckling. So D by T is less than 67. No need to check. Let us check it first. So what is D? Depth is overall depth of the I section 600 minus the flanges we have to remove. That's the web 2 times 21.3 plus 17. Okay, we get it as 523.4. Thickness is 11.2 mm. So D by T, if you check it, it is 46.7. So 67. So no need to check. So clause number 8.4.2.1 talks about this check for web buckling. If it is there is a need for check, there is a formula will be there. You can just substitute and check for web buckling. Okay, last step is step for check for deflection. So this page number page number 32, I think page number 31 or 32, table number 6, table number 2, I think. Sorry. Yeah. Page. Yes, here is the deflection limits. You can see page number 31. Here it talks about this. What is the maximum deflection we have to consider while finding out this loads. Okay, average loads. So based on that table, so it should be limited to L by 250. The working load, for a working load, deflection to be limited to L by 200, 250. So for maximum deflection, so this is our figure, right? So let us draw the conjugate beam with M by E diagram. So these are the values we got. Okay, so initially this is 286 by EI. We got the load values. So M by EI diagram we have drawn. This is a conjugate beam. So the reaction in conjugate beam is half of the total of the M by EI diagram. This is very symmetrical section, right? Even there is a gradually varying load up to here, gradually varying load up to here, uniformly distributed load here. But however, it is symmetrical. So we can just half of the total M by EI diagram. So half into base into height, half into base into, just base into height. This is the rectangular portion and this is half into base into height is the triangular portion. So from that you will be getting it as 715 by EI, a reaction as a conjugate beam. So maximum deflection occurs at the mid span. So how will you find out the moment? So at this part, you have to find out the moments. This 715 into distance, this into distance. Okay. So that distance is, you have to calculate it as triangular load. The load itself half into this base, that is how much? 1.5 into 1.5 into height, that is 286.EI. That is the load multiplied by center of gravity of the distance up to here. That is how much? 1.5 by 3 plus 3.5 by 2. So all were clearly mentioned here. You just check it, and you will be getting that moment itself is the deflection. As a conjugate beam we have already seen in strength of material concepts. Okay, so you got E, E value is 2 into 10 power 5 Newton per mm square moment of inertia. As you have written in the properties, this is 1207.808 into 10 power 6. Now you can find out the deflection in terms of, in pure numericals as 5.75 mm you got it. So let us check the permissible deflection. L by 750. This is L by 750. Gantry crane girder. This is span by 750. L is length of the gantry girder 6500 by 750. 8.66 mm. This is a permissible. You cannot have this deflection more than this 8.66. It is within the limits, so it is satisfied. So what are the sections we have chosen? This compression flange ISMC 300 and this gantry girder I with I section ISWB. Indian Standard Wide Beam 600 is good. Thank you.